Hello, everyone. This is our lesson for 6.1 and 6.2 class prep, and this is an introduction to hypothesis tests for the mean. I'm going to try to give you some big picture stuff. You'll have other stuff in your notes, but I'm going to try to give you some big picture stuff today, and then when you come to class, I'll have some handouts, sort of like we had for confidence intervals, some tables that kind of help you keep your different cases straight. And you'll see those little tables will show up in this. You don't need to fill those out in your notes, but just know that when we get to class, you'll be filling those out. So our goals today, we want to learn about hypothesis testing in general. What question does a hypothesis test answer? How do you interpret it? And how do you use RStudio to perform a series of hypothesis tests? I'm not sure we're going to get to all that. We'll see. So this is a new tool, right? This is another big idea in statistics. So we had this estimation, which we used like confidence intervals to estimate things. Now we're doing this testing. So confidence intervals simply estimate parameters from a population based on sample data. But more commonly, people really want to answer specific questions about a population, like, this is from last year, you can tell, but like, was President Trump's overall approval rating above 45%? We want to know that about the entire population of registered voters, not just the sample. Or is the GPA for all Doane student athletes above 3.0, not just for the sample, but for the entire population? Is the average GPA for a Doane student athlete worse than the average GPA for a non-athlete? I think I told you that one in class. Do women engineers get paid less than male engineers on average? And, does the tartaric acid concentration in white wine differ for wine before and after a cold stabilization process? So it's sort of a quality control kind of question. So notice they're like questions now, not just like estimate, right? They're like questions with a number involved. Okay, so this is kind of, you're going to see there's going to be 4 steps in any hypothesis test that you're going to have to show. But this is just kind of the first step. So you're going to write, you'll see up here, I have these symbols. You're going to write a null H sub 0 and an alternative hypothesis based on the problem's context. This is setting up the argument, right? There's an argument. It's either this, like the mean is either this, or the proportion's either this or this, okay? So you're setting up the two sides of an argument. You always start with the alternative hypothesis, and it should mimic the question and align with the evidence in the data, okay? So the alternate aligns with the evidence in the data. The null hypothesis is the opposite. You'll see how we do this. We set up these 2 opposing views. So if we said, is President Trump's overall approval rating above 45%? We start with the alternative. So you see we have this H0 versus H1. We start with the alternative, and we write, that's a proportion, is the percentage greater than 45%, 0.45, all right? And then the null would be the opposite, less than or equal to 0.45. Second, is the GPA, average GPA for a Doane student athlete worse than the average for a non-athlete, okay? So now you have to think about those signs again, right? Like the positive and negative in a difference, right? Is mu A minus mu N, that would make the mean for athletes bigger, smaller than the mean for non-athletes if it was less than 0, right? So is the mean for athletes minus the mean for non-athletes less than 0, negative? That's the question here. I don't know that we have evidence of that, right? But if we were asked that question, we might set up this test this way. And the null is the opposite, greater than or equal to. And then this last one about this acid concentration in white wine, right, before and after some process, right? So then we would have the mean for before minus the mean for after, right? Different, not equal to 0. So differ is not equal to 0, right? And then the opposite is equal to 0. So setting them up correctly is one of the big problems that students have. not that hard. You can tell it wouldn't be that hard. You just spend a little time on it, right? But you need to make sure you set up your process correctly. Okay, let's go on. And so in any of these tests, we must make a decision between two choices. And one's sort of a weird choice, all right, based on the sample data. So this is like, I'm moving ahead, right? We're going to make some decisions, right, between H0 and H0 and H1, all right? And I just want you to kind of get the idea behind hypothesis testing. This is the big idea part. So just follow along. This is a story, okay? So I'm going to tell you a little story, okay? So suppose we believe that student athletes have an average GPA above 3.0, okay? And let's say somebody's like, hey, student athletes, they're not good students. I hear that sometimes from new faculty members. I'm like, actually, they're not. They're really good at Doane, okay? So, all right, so let's say somebody, right, I want to prove that student athletes have a GPA above a B average, okay? So we wish to prove H1. This is what I believe to be true, that the mean for athletes is greater than 3, all right? So notice that's what I would do. That's what I would set up. All right, so notice I'm not setting up the H0. We know that would be less than or equal to 3. But let's talk about what we would actually do here. Sorry that I just messed up the way the screencast was centered on the slides by clicking on the slide. I won't do that again. Okay, so let's talk about what we would do to try to prove that, okay? We take a sample of some size and calculate the mean and the standard deviation, right? So you're starting to probably understand what it takes to do things in statistics, right? So let's just talk about, what if we took a good sample and the sample mean was 3.92, right? Wouldn't you just be like, clearly, student athletes are really smart. They almost have a perfect GPA, right? We would have lots of evidence towards this hypothesis that the mean is greater than 3, and right, that would prove it for sure. What if the sample mean was only 3.17? That's closer. So maybe this is true in the population, but we're not sure. We would need to kind of test it. What if the sample mean was exactly 3.0? Wouldn't you be kind of bummed out? Like, you'd be like, I don't know that we can prove this. So it doesn't look like we have any evidence, and we would call that failing to reject H0. We don't have any evidence in the right direction. And what if the sample mean for athletes was 2.92, below 3? We would say we fail to reject H0, okay? Or reverse the hypothesis. Maybe we could reverse the hypothesis and test, see if we can prove that it's less. All right, so our two decisions are reject H0, which means we conclude H1, or fail to reject. So make sure you get this decision thing in there. We fail to reject H0, which means you can conclude nothing. Notice it's sort of like hypothesis testing, right? Or confidence intervals, right? Remember, we had one situation where we're like, we can't prove it. We can't, or, we can't say anything about it. And then on the other hand, right, sometimes we had something we could say. Okay, so that's kind of the big idea. So let's actually take a sample. So we take a sample of 40, and let's say we're in this situation where it looks like we have a little evidence, right? Sample mean is 3.17, standard deviation 0.4. And what we really need to do is test these values and see to see if this really shows evidence that the true population mean is over 3.0, okay? So here's how the process works. If you're a math major, you'll recognize this really as a proof by contradiction. I bet you thought you might never have to hear that again. All right, but assume the population, what we're going to do is we're going to assume the population mean is 3. And then remember, we had the central limit theorem, and it said that the sample means value would be normal with mean 3, and the standard deviation, like S over square root of n. You might think back and see that those are a little familiar. So the question is it likely that this sample mean of 3.17 came from that distribution? If it's yes, then I guess we can't show that the true mean is really over 3.0. But if it's no, if this is a weirdo, x bar equals 3.17 is extremely weird compared to a population of with mean 3, then there's a problem. And so here's the problem. Either our sample was messed up, right? It was just unusual, or that assumption that the mean was 3, right, is wrong. And really the mean should be over 3, which would make 3.17 more probable. Now we'll talk about this a little more in class, but this is what's going on. We make an assumption, and what we're trying to show is that that assumption is wrong and that it should be closer to what we saw in the sample. So if we standardize that x bar value, 3.17, and we'll see how weird it is, right? So the z value, remember, you take the score minus the mean over the standard deviation, right? We do 3.17 minus 3 over 0.4 over square root of 40. You get 2.69. That's a pretty extreme z value, right? It's almost out to 3. In fact, we could use the z table and show that only less than 1% of the values are larger than this. And we already said we took a good sample. So this value, 3.17, sheds doubt on our assumption that the mean is equal to 3. So we get to conclude that the mean is greater than 3. So this 3.17 is fine. All right, it could prove our point that student athletes have a mean GPA over 3.0. Here's the good news. We just did a bunch of calculations. RStudio will do all the calculations for you. You don't have to get out a z-table or anything, but you do have to understand the situation you're in, large, small samples, independent, paired samples, the normality stuff, just like you did in confidence intervals. So all that work you did in confidence intervals, it all is the same here. And you have to understand how to outline the steps of the process. Okay, so it's not going to be, RStudio doesn't do any interpretation. It just, you've seen what it gives you, right? It just shoots out a bunch of numbers at you. All right, here's the 4-step process, and let's make sure you get this written down, okay? This is necessary. For every test of hypothesis, we're going to use the following 4 steps, okay? And we've already discussed some of these. So your step 1 is going to be, right, state an H0 and an H1 using the symbol mu, or it might be a difference in means, you'll see later, okay? Then you're going to run t.test. Notice it's the same code, right? Right? So we usually call these t-tests, and record t and a p-value, all right? So you're going to see a t come out and something called a p-value come out. We've actually saw both of these values in that previous example. I didn't necessarily call them that. And then you're going to make a decision, reject H0 or fail to reject H0. Notice it's not reject or accept. It's just reject or fail to reject. Notice that fail to reject, very wishy-washy language on purpose, sort of like guilty or not guilty, right? Not guilty doesn't mean innocent, right? Fail to reject doesn't mean that H0 is true. It just means we couldn't show it to be true. And then you're going to interpret in language for my husband. All right. These are usually pretty easy because these problems will start with a question, and really you just answer the question. So the interpretation is actually probably a little easier than it used to be in confidence intervals. I think I'm gonna skip ahead and just kind of show you an example. All right, here's an RStudio example. And then when we come to class, we'll do one. Is there evidence that the average math engineering student has fewer than 4 siblings? Use a 5% significant level. So if we wanted to do that, we would do a t-test, SIB, alternative less, and mu equals 4. So, right, that's going to be the code. The reason is because H1, we're going to set up with mu less than 4. That's because the sample mean, all right, was 2.5 in that data set, okay? And we asked do they have really an average of fewer than 4 siblings, okay? And that's for all average math and engineering students. And this is greater than, okay, as an opposite. And that's what you would run. And then everything's showing up in here. Okay, I'll see you in class.